Let's think a little bit about the molecule sodium chloride. If we look at the periodic table right over here, we see that sodium is a group 1 element. It's an alkali metal. It has one valence electron. It's also not too electronegative. It's sitting here on the left-hand side of the periodic table. We know the general trend for electronegativity is that it increases as we go to the top right. So these elements over here generally like to hog electrons. These elements over here generally like to give away electrons. These are electropositive, these are electronegative. So sodium right over here with its one valence electron, it's a very good candidate for giving away an electron. On the other side of the periodic table, we have chlorine. Right over here. It is a group 7 element. It's a halogen. It would love nothing more than to gain an electron so that it can get to the magic number of 8 valence electrons. It is very electronegative. So what you can imagine would happen is if these two things were to interact, the chlorine would nab sodium's extra electron over here, and it would become the chloride anion, and then sodium would become the sodium cation. Cation just is a positive ion. Anion is just a negative ion. And so this one right over here is now positive. Sodium is now positive. Chloride is a negative ion. And so they're going to be attracted to each other, and they're going to form this ionic bond. So this right over here is an ionic bond. Now let's think about something that's not ionic. That's more where the electrons are not being fully nabbed from one atom to another, but they're being shared. And one of the most famous examples of that is water. So we know water is H2O. You have one oxygen bonded. Each water molecule is one oxygen bonded to two hydrogens. And these two bonds are covalent bonds. In each of these bonds, you have a pair of electrons that are being shared by both the hydrogen and the oxygen, being shared by both the hydrogen and the oxygen. But we also know that this isn't a completely equal sharing of the electrons. We look on the periodic table here, oxygen is far more electronegative than hydrogen is. And so because of that, the electrons are going to, in these two bonds, are going to spend more time around the oxygen than they are going to spend around the hydrogens. And we've seen this before. This would give the oxygen end of the water molecule a partially negative charge. That's the lowercase Greek letter delta. We use that for the notation of partially negative. And on the hydrogen ends of the molecule, we're going to have a partially positive charge. Now, this is the reality, but as we'll see later on and in future videos, it's sometimes inconvenient to have this kind of partial messiness. And so what I'm going to do right now is introduce you to what is fundamentally just an intellectual tool. It's just a convention that chemists have invented that allow us to get our heads around a lot of reactions and allow us to think about how is a reaction likely to occur. And that intellectual tool is the idea of oxidation states. The idea of an oxidation state. And what the oxidation state is even if you're in a situation where you have covalent bonds, you say, well, look, I understand. Those are partial charges. These are covalent bonds. The electrons are being shared. But I don't like this partial stuff. I want to just assume, hypothetically, what if these were ionic bonds? And you say, well, okay, if these had to be ionic bonds, then the oxygen would nab the electrons from these pairs. And so the oxygen would have a fully negative charge, a -2 charge, and the hydrogens would have a fully positive charge, each. And so if we were to write down the oxidation state, or the oxidation states for the atoms in the water molecule, let's write that down. So H2O, we would say that oxygen has an oxidation state of -2, and water, each hydrogen atom has an oxidation state of +1. of plus 1. And notice, the whole molecule is neutral, and these things cancel out with each other. Positive 1, that gets you to positive 2. Then you have negative 2. They cancel out. Now, the one thing, I keep saying this is negative 2, but I wrote the negative after it. If I wanted to write positive 1 as an oxidation state, I would actually write it as 1 positive, although you can assume that if someone just writes the positive. And this is just a convention to write the sign after the number when we are writing actually ionic charges or oxidation states, because an oxidation state is nothing but a hypothetical ionic charge. If you really had to, if you were forced to assume these aren't covalent bonds, but these are ionic bonds. As once again, I want to stress, this is the reality. These are covalent bonds. These are partial charges. The oxidation state, intellectual tool that's forcing us to pretend like these are ionic. These are ionic bonds. And you might say, okay, well, this kind of makes sense right over here. This involved oxygen in some way. That's why it's called oxidation states. And that's how I initially conceptualized it when I first learned about this. You said, well, look, hydrogen lost, each of these hydrogens lost an electron to oxygen, so it makes sense that we say that the hydrogen, each hydrogen got oxidized. So hydrogen oxidized by oxygen, It makes sense that oxygen would oxidize something else. This got done to it, some operations, the charge was taken away by oxygen, so it got oxidized. Now the other term on the other side of oxidized is reduced. And the word reduced really comes from the idea that oxygen's charge has been reduced. So we could say O, or we could say oxygen has been reduced by the hydrogens, by the hydrogens. And so there's a temptation here to say, okay, this must always involve oxygen in some kind because it seems to begin with the same words. Well, that is not the case. Let's take, for example, if this is an aqueous solution, hydrofluoric acid. Hydrofluoric acid right over here. You have a hydrogen covalently bonded to a fluorine. Now, just like we saw in water, fluorine is one of the most electronegative elements. It's going to hog the electrons in this covalent bond. So this is going to have a partial negative charge here. This is going to have a partial negative charge here, and this is going to have a partially positive charge. But if we were going to think about it in terms of oxidation states, we would say, okay, let's, when push comes to shove, if this had to be an ionic bond and not a covalent bond, what would be the charges on each of these atoms? We say, well, in that case, hydrogen would lose an electron and it would have a full positive charge, and fluorine would gain an electron and have a full negative charge. This is a hypothetical. Once again, the reality is they're partial. It's a covalent bond. But the hypothetical one is a full positive charge here and a full negative charge here. And so we would say that the oxidation state in this molecule for hydrogen is +1, and the oxidation state for fluorine in this molecule is -1. And we would say that the hydrogen has been oxidized, and we could even say it's been oxidized by the fluorine. And we would say that the fluorine, because its hypothetical ionic charge has been reduced, we would say fluorine might be reduced. And you would say, hey, wait, look, oh wow, we're using the word oxidize even though there is no oxygen to be seen here. And one way to think about it, if someone had told you that you had been Bernie Madoff, that doesn't necessarily mean that you interacted with Bernie Madoff. It means that someone did to you what Bernie Madoff would have done. Someone took your money, told you they were going to invest it, and then put it into a Ponzi scheme. Even if that person is not Bernie Madoff, you could say that you have been Bernie Madoffed. So here, fluorine did to hydrogen what oxygen tends to do. It took an electron away. It oxidized the hydrogen. Now, that's how I tend to remember it. The oxidized is if something has been oxidized, It's losing an electron. And what I think about it is, well, that's what oxygen would have done to you. Oxygen is very electronegative. It tends to take electrons away from other atoms. Now, there are other mnemonics that you might see for remembering what oxidation and reduction actually represent. And I'll introduce those to you just because they might be helpful, and they are introduced in a bunch of chemistry classes. One of the mnemonics is Leo. Leo the lion says grr. Leo the lion, and I'll write says in lowercase here because it's really not relevant, but Leo the lion says grr. Grr. And this is to remember that losing an electron means you are being oxidized, or losing electrons is oxidation, and gaining electrons is reduction. So that's just a mnemonic. Another one that's often used is oil rig. Oil rig. And this essentially, oxidation is losing electrons, reduction is gaining electrons.